After years of engineering and construction, the FLNG vessel is finally towed out from the shipyard to its permanent location, potentially hundreds of kilometers offshore. But this is where the real nail-biting begins. The complex, weather-sensitive work of marine installation kicks off. We're talking about connecting the mooring system, hooking up subsea wells, and setting this colossal vessel permanently in place. Make a single mistake during this final positioning, while that could lead to a delayed startup costing millions of dollars every single day.
Yeah, the stakes are absolutely staggering here. Like they say in the industry, one mistake here can mean a vessel left adrift. It's a massive, high-pressure operation. We are looking at the immense physical and financial reality of taking a floating liquefied natural gas, or FLNG facility, from the safety of its shipyard out to a highly volatile, deep ocean home. Welcome back to The Explainer. Today, we're diving straight into Module 9, FLNG Installation and Hookup, the high-stakes voyage. We're breaking down exactly what it takes to permanently moor and connect one of these massive facilities. Let's get right into it. Here is our quick roadmap for today. First up, wet tow and sail away. Then, turrets and mooring installation. Third, risers and umbilicals. And finally, marine corrosion protection.
So, Part 1, wet tow and sail away.
Once the vessel actually passes its harbor acceptance tests, it's prepped for a wet tow. Basically, it's towed across the open ocean by a fleet of heavy-duty ocean-going tugs. Now, depending on the field location, this trip can take weeks, sometimes even months, so you absolutely need a rigorous tow management plan. This covers the precise tug selection and configuration, emergency disconnect procedures, and constant stability monitoring. You also have strict weather window requirements and regular condition inspections done right on the deck by what we call riding crews. To keep everything safe during the journey, all the hull openings are tightly secured, temporary sea fastenings for the topside equipment are verified, and the vessel's systems are put into standby mode. Moving on to Part 2, turret and mooring installation. Long before the FLNG even shows up, specialized anchor-handling vessels arrive at the site to prep the seabed, and they use something called suction piles. These definitely aren't your grandpa's boat anchors. We are talking about massive steel cylinders that are literally driven deep into the ocean floor using suction pressure. They act as this incredibly strong, permanent foundational anchor for the whole facility. The installation sequence itself is pretty wild, honestly. It's this crazy contrast between colossal, heavy machinery and microscopic precision. First, those specialized vessels pre-install the suction piles. Next, they pre-lay the massive mooring chains right from those piles. Then, when the FLNG finally arrives on location, work-class ROVs, or remote-operated vehicles, team up with anchor-handling tugs to connect those giant chains to the FLNG's turret chain tables. Once connected, they have to verify and record the chain tensioning to make sure it matches the exact design pre-tension from the mooring analysis. All right, Part 3, riser and umbilical connection. Okay, so the vessel is permanently moored. Great. But it's basically useless if it isn't hooked up to the gas, right? Making that connection involves two very distinct systems, both installed by specialized vessels. First up, the production risers. These can be rigid or flexible, and they're the actual pipes doing the heavy lifting, bringing the gas up to the surface. They connect at the seabed to the flow lines from the wellheads, and then route all the way up to the turret connection point. On the other hand, we have the umbilicals. Umbilicals are essentially the nervous system of the entire operation. They are complex bundles of hydraulic, chemical injection, and electrical lines. They allow the topside crew way up on the FLNG to remotely control the subsea trees and wellheads deep below. Down at the seabed, they connect to a subsea distribution unit, and at the top, they plug right into the umbilical termination unit on the vessel itself. Now, pause and think about this for a second. We are dealing with incredibly high pressures, deep underwater. So what happens if there's a leak at one of those subsea connections once the gas starts flowing? Well, because of that extreme risk, absolutely every single riser and umbilical connection has to be perfectly pressure tested and function tested before handing anything over to the commissioning team. Because let's be real, a subsea leak is an absolute nightmare. Fixing any kind of leak at the subsea end requires deep-water ROV intervention. It leaves absolutely zero room for error, mostly because it is incredibly expensive and insanely time-consuming. Pulling off a fix down there eats directly into the project's bottom line and delays the entire startup. Finally, Part 4, Marine Corrosion Protection Systems. So the facility is fully hooked up. Awesome. But now it faces its next huge challenge, just surviving for decades in a highly corrosive saltwater battleground. To do this, the vessel uses a multi-layered defense system. The hull gets coated in multi-layer anti-fouling and corrosion protection paint, backed up by scheduled underwater cleaning. For the seawater piping, they use internal epoxy coatings, rubber-lined sections in the high-velocity areas, and titanium heat exchanger tubes in the seawater coolers to completely prevent crevice and pitting corrosion. But my favorite part is the cathodic protection.
The vessel actually uses sacrificial aluminum anodes on the hull and the submerged risers. These are literally pieces of metal designed to corrode, so the vital steel of the ship doesn't have to. But they supplement that with something called ICCP, or Impressed Current Cathodic Protection. Basically, it's an active electronic system that pumps electrical currents right through the hull to actively stave off corrosion. It's basically high-tech oceanic armor. With the FLNG permanently moored, all the subsea connections perfectly made, and that oceanic armor fully active, the marine installation and hookup phase officially wraps up. The engineering is built, it's sitting there, but the true test is just beginning. As we move into the final phase, the goal shifts entirely to bringing every single system to life for the first time, safely and systematically.
And that sets the stage perfectly for what comes next. In Module 10, we are going to cover commissioning. This is where process fluids finally enter the system. It's where years of intense engineering and construction are ultimately validated. Honestly, it is widely considered the absolute most exciting and, without a doubt, the most stressful phase of any energy project. Will all those connections hold under pressure? Join me in the next explainer to find out.